Uh, so great. So let's get started. So the system seems like a little finicky today. There's like a loose wire or two someplace, but hopefully now that it's going, everything's going to be okay. So let's see. So today I decided to mostly to kind of do a couple of things. I'm going to start the little review of trying to be the difference between confidence intervals and hypothesis testing. I think may put these together. I think some people have been asking about this, but most of this will be going through examples of these in mostly in R. And then if we have time, I'll talk about some stuff like permutation testing, something advanced at the end. But if we don't get to that, that's gonna be fine. So yeah, if you look at the schedule, so a couple things. Oh yeah, so it's updated. So like homework 7 is out. I've got some printed out versions of homework 7 up front if you want some. So that's due, let's see, next week on Tuesday. I'm not allowed to have assignments be due after the last day of class, but we'll be a little flexible on that. Okay, and the other thing is I posted another practice exam. I also have printouts of this practice exam, including a few in some pink purple color because that's what was in the printer. So those are linked off of here at the bottom. This is practice 2. Practice 2, if you look at this, this is the total number. If you can get these after class, that would be great. So this is 160 points is practice 2, and it kind of tries to be more kind of trying to cover everything. So the final exam is going to only be 100 points, right? So this is kind of longer than the final exam. If you finish this in 2 hours and feel pretty good about it, well, then you're on a faster pace than you need to be for the final exam. Okay, but this will give you a sense of what it's like. I just made it. I don't have solutions yet. I bet if you ask nicely, you might be able to get each TA to solve a page and then post the final thing online. Yes. Okay. So this will give a summary of the entire semester by looking at that. The final exam location was moved. Okay, I just learned about this yesterday afternoon. I thought it was going to be in here, and the room here is pretty nice. The desks are kind of small, but pretty good. We're going to be in the was it SBH auditorium, or is it SHEB? What? No, not this room is ASB. Yeah, so the tall building that so just south of the library. Is there a reason why it's called the Tower of Terror? Oh, okay. So it's not. All right. There's nothing hopefully too scary, but I have not been there. I just found out I had meetings all day. I haven't had a chance to go. I'll plan to check it out and provide a little bit more guidance in one of the last few lectures. But the room is at least as big as this one, so we'll be able to spread out, and so we're gonna just fit everyone in that room. So I think that should be okay. It's the big auditorium. Hopefully, I have more specific directions. So before that, but don't come here. It's probably at least a 5-minute walk from here. So if you start here, you'd be 5 minutes late to what you're like what time you're planning to be there. Yeah. Is what? Yeah. So so there are 3 lectures left, including this one. I'll plan to record all of them, including the review. Yeah, the review, I'm just going to kind of go over kind of like, so lecture style, everything we covered over the semester was the plan. But if you have questions you want to bring to that, that's also fine. If you want to start by asking me questions, say about like the practice final or something, we can go over that. That's fine. But if not, I would just go through the material for the whole semester. And if you understood everything there, you should be able to do great on the final. Yeah. It would be fair to ask you some fairly very simple, straightforward questions in R, but nothing so complicated, right? There's so like if you get like something very simple wrong about like the syntax or something, that's not the sort of thing I want to ask, right? It's more of like, can you compute this sort of thing in R, something like that, right? So, but I won't expect something super specific in R. Okay, so but it'd be fair to ask something about R. That's what we covered, but I don't want you to have to memorize. You know, I don't expect you to be kind of a complete R programmer at like the end of this course. Okay, but I'm not going to check if anything compiles, and yeah. Oh, so yeah, someone asked the same thing online. Great. So okay, yeah. Those seem like, yes, so something specific like that we use multiple times would be something that might be something I could ask on the final, right? So this is how you look up in those tables for the t distribution or the norm distribution. Oh yeah, so what the student asked in the class, would qt or qnorm, those things that allow you to look up in the normal CDF table or the TDF, so CDF table, maybe how to use those would be kind of something I could ask. Again, I don't want to be a stickler about the specific of the formatting, so I wouldn't ask like a long complicated question, but I could ask some variant of that. Like, here's part of the code, I leave this one thing out, maybe you have to fill something like that in. That seems like something reasonable I could ask. I've not created the final yet, so I don't know exactly what's going to be on it. Yeah, and there's a question about, so the cheat sheet, you will get one front page and back. I want this to be kind of handwritten. If you want to do it on a computer, it's fine, but I don't want you kind of just like taking all the notes and creating like a microfiche or something like that. Good people do that in the past, and I think that kind of defeats the purpose. The point of it is I want you to take the time to go through and kind of select out what you think is the most important thing and either retype it or rewrite it. That process, I think, is an informative way to study. And that's, you'll write down the key things on that cheat sheet and you get to bring that to the exam, and then helps you remember them and look them up. And if you just copy and paste a whole bunch of stuff without thinking about it, it's not going to have like the same effect. So I don't want you to do that. If you want to do this in small groups, that would probably be okay. Okay, but I don't want like half the class to have the same cheat sheet. Okay, yeah. Yeah, I was thinking, I haven't finalized. Yes, I'm gonna say, I'm gonna ask you to turn in the cheat sheet at the end. Yeah, so if you have a cheat sheet, if you have scratch paper, I won't ask you to staple it, but I'll ask you to turn them in so I can kind of, see what the cheat sheet is. Yeah. Yeah, I was thinking of actually having a question on the exam about did you make a cheat sheet, but I decided not to do that. But I'd still like you to turn in the cheat sheet, I think. Yeah. So, okay. Does that help with the questions on the exam? All right. So, oh yeah. So quiz number, 13, that's going to be, so this week, we're not going to have a whole bunch of like super new material that is like super essential for the course this week. It's going to be mostly review of some, I mean, there'll be some stuff from today, which I think will probably is going to show up on the exam and in homework 7. But quiz 13 instead, I'm going to give you a chance to get some points back. It's going to be about feedback. So I want everyone to fill out the course feedback form. So here's the deal on that. If 70% of the course fills out the course feedback, I will give everyone 100 on quiz 13. If 85% of the class fills out the course feedback, then I will not only give everyone 100 on quiz 13, but I will allow you to drop 3 of the quizzes. Okay. Okay. So that seems like a good deal. So I encourage you all to do that. Encourage your fellow classmates to do that as well. So that's what quiz 13 is going to be about. If less than 70% fill out the course feedback, then I'm going to drop quiz 13. Okay, I'll take it off the grading. I'm not going to give everyone a 0. But that's kind of the other option. But I felt I don't think I'm supposed to do that. So then we'll take quiz 13 out of the average. I have it left open. I think I changed it, or maybe it's not. But it'll be open until like the end of like roughly the last day of class. So you don't have to necessarily do it this week. You can wait until to see if you liked my review lecture before you fill out the feedback if you want to. But so yeah, so that's what quiz 13 will be. Yeah. Yeah, I'll do this on Canvas. We just kind of finalized this today, and I think I updated the text on quiz 13 and said notify users this has changed, but I'm not sure you could see it yet. But I will post this on Canvas. You can also post it on Canvas if you want to remind everyone to take it. But so okay, yeah. Yeah, I'm not sure if you can see it yet, but I put like links and everything in there. And there's on the Canvas page, there's a link directly to course feedback for this. So for this course. Yes, okay. Great. So that's the schedule. All right, let's get to the material for the lecture. So okay, so I'm going to talk about kind of confidence intervals versus hypothesis testing, and I think these are very interrelated views. And so let me just kind of give you kind of an overview of, like, in general, there's going to be, we're going to think about collecting some data, IID from distribution, and we're going to like these continuous parametric distributions that have a parameter that describes the whole distribution, because then we can just learn this one parameter, right? And so this makes it convenient. Instead of like a discrete distribution where it can have a lot of stuff, we're just going to learn this one parameter. Machine learning mostly does this. Well, it did this until about 10 years ago. Now they have like 100 million parameters in them. And so it's not really this anymore. But, you know, for a long time, machine learning was similar. You just learn the parameters of the function. And so usually this will be the normal distribution. And you may or may not know the variance, right? And then you want to think of a statistic, okay? And this will be T which will be a function of x1 up through xn. And again, so usually we're going to have this as xn bar, which is 1 over x, which is the average of all of those xi values, right? So so then there have been 3. So then this is trying to, the point of this is to try and see if we can estimate so this parameter, right? So, or can we estimate so this this parameter theta, and what we would do is we would set theta equals to t, and here this would usually be mu hat equals xn bar. So that, and then there are 3 ways we could approach this. One is we could look at the the bias of this parameter. If this is unbiased, then it means that the expected value of this is equal to so the true value, and then we would say it's so this is efficient if the variance of this is so small. Okay, so the first thing we looked at was just the estimator. We're saying we're going to take this data and we're going to take the average of it typically, and we're going to say how good does that estimate the parameter of the distribution. That's all we need to say the whole distribution. Okay, so this is the first way. The second way we looked at was the confidence interval, and we said, well, without just looking at the variance, oh yeah, and we said here that for these guys, the expected value of xn bar was equal to the mu, so it's unbiased, and the variance of xn bar equals the true variance divided by n. So this was going down, right? So we looked at that the true variance was going down. With the confidence interval, what we were doing is saying, well, we have this estimator, but what's the probability that it's close to the true value? Instead of just saying, well, in expectation it's close, what's the probability it's close? And so what we did is we defined these that these ln theta, so Rn, okay, these were these random variables, so that this was equal to 1 minus, so alpha, okay, and these ln equals, let me just write this in red, it's going to be the true estimator xn hat plus or minus either this z alpha over 2 times the true standard, or the standard deviation, right, of that estimator. That's the left-hand side, so this is minus, and the right-hand side is the plus value. So we could take that true estimator, you'd say, well, what's the probability that it falls in this range? And we kind of define this close. This guy is defining what it means to be close. That's what it means to be close. The other one is going to be the hypothesis test. All right, and so we're going to say, well, instead, the hypothesis test is a little bit different in that we're going to suppose we have a guess of what the true value is, and we're going to say, is it going to be close to that guess, right? So this is asking, is is xn bar close to, so the guess. So like mu, right? So mu would be like a, so would be like a null hypothesis, right? So, okay, let me draw a picture. So the one thing is that xn bar is a random variable, okay, and then lowercase xn bar, this is so lowercase, okay. On the exam, you should be able to clearly see if it's lowercase or uppercase. This is going to be a realization of so the data. And the thing is, I can plot specifically xn bar here. This is an actual observation, right? So sometimes I use t as like an actual statistic. This guy is an observation, and so actually the average of the data. Okay, so it's actually, I took a bunch of observations and I took their average. And so now I can think of having a true value. So in any case, this is the realization. And there's another point on here, which is the true parameter. Okay, and so now to do a so if this was the true parameter, then there's going to be a distribution associated with the actual statistic. So make this a little bit wider here. Okay, so usually this is going to be symmetric, right? And so this is the distribution of xn bar under the true parameter, mu. Okay, but then we make an actual observation, which in this case was out in the tail, right? So there's some kind of, tail here. And so this actual observation is here, and we'd like to put a confidence interval around this. And so we're going to say, well, given this actual observation, we're going to put some interval ln, so rn, right? And we're going to say, well, I'm going to put these. So these are these values ln rn don't. Okay, so these don't actually exist. These are like like random variables. So and actually, every time I draw a random sample, this is a rare case. But in another case, it's going to be out here, right? And we have this distribution of these different intervals I'm going to find. And so what I'm doing is I'm doing some algebra to change the distribution around mu to put this the distribution around xn. So I could say that let's see. So I can say that the probability that that xn bar, that xn bar falls in is in, so the interval of the true value mu plus or minus the this z alpha over 2 of, that's here, z alpha over 2 of this standard deviation of, so xn bar, this is equal to, so like 1 minus alpha, and that's saying if I took this and I went out this distance, what's the probability that xn bar actually, so like fell in here. If I want to fall in, so 95% of the time, then I should have, so that the probability it falls outside of here is alpha, so divided by 2 on each side. This one is alpha divided by 2. This is alpha, so divided by 2. But this is not so useful because I don't know what mu is. So I have to do some algebra and put these around xn instead. So I say if it's in there, so I can instead add and subtract this term here from xn bar instead. And so I can say this is equivalent to the probability that mu is in xn bar plus or minus z alpha over 2 sigma, so square root n. Okay, so this is equivalent by adding and subtracting this kind of this term I've circled in red from, so from both sides. So I'm putting those confidence intervals around, so xn bar instead. So it's it's kind of the same expression, but I've done some algebra to put it around the xn bar, and that makes the ln and the rn actually these like random variables. So they're things I can then analyze the probability of, and I say what's the probability the true parameter value fell inside this interval. Say with 95%, it fell inside this interval. In this case, it did not fall inside the interval, but that's 95% of the time because this true case is here. If I put this ln and rn, instead I put it, so if I subtract, so this distance here is exactly z alpha over 2 square root n. And if instead of saying if xn bar minus z alpha over 2 sigma over square root n, if I subtract that, is mu less than that, it's the same thing as if I add that to mu, and is that term, as that value kind of less or equal to xn bar, right? So I can switch where the intervals are. And so when I put a confidence interval, I make an observation, and then I say, okay, it's probably inside this range, the true value, okay? But now if I'm doing a hypothesis test instead, I'm saying, well, I'm going to assume, make a guess from you, and then say, given I made a guess from you, what's the probability it's kind of outside this, it's outside the confidence, it's outside the confidence interval, right? And if the true observation is in the tail, then that's when I'm going to reject the null hypothesis. Okay, so let me try and summarize this. A confidence interval and a hypothesis test. All right, so so you try to find region so likely to contain mu. Okay, and in this one, you make a hypothesis of choice of mu. All right, so the hypothesis is not informed by data. Okay, the confidence interval is the center of the confidence interval. Okay, the center of the confidence interval is informed by data. Okay, here the center of the null hypothesis is from guess. So in the confidence interval, I'm saying I'm going to observe the data, and I'm going to say how likely is the true parameter to be close to the data I observed. In the hypothesis test, I'm going to make a null hypothesis of what, before I collected the data, what I thought it was going to look like. And then I kind of judge of whether that is if that is going to be supported by data. So this gets a range of how close is true value likely to be, and this says how likely is mu zero to be a like the true value. Okay, so this one gives you a guess and say, I think the guess is probably near here, and tells you how close is near. That's the confidence interval. The hypothesis test says, well, if you had another thing, I can say, well, that seems reasonable, or it does not seem reasonable. Okay. One other thing, the confidence interval is usually two-sided. That means I take a guess and I say, here's the distance on either side. And that means you actually have half of your probability of like that you get the wrong thing above and half below. The hypothesis test is usually one-sided. Okay, so usually I say there's mu zero, and then the alternative hypothesis is that there exists a better mu one, which is like greater than mu zero. So I only need to kind of try and rule out it on like one side. If it happens to be smaller on the, if I think, okay, something's probably larger and it happens to actually be smaller, I don't worry about this case. So when I'm computing these, there's this Z alpha value, which we have to compute. And for the confidence interval, I often do Z alpha over 2 because I need to put alpha over 2 on either side. For the hypothesis test, I would just use like Z alpha, and then I would only kind of, I would be able to say, so I could do this, and I could say, would be like, this would be Z alpha, because I could only say that this whole region here has an alpha probability under the curve. So usually hypothesis tests, you only look at one side. Okay, but they're really kind of the same sort of object. We're using that as we accumulate lots of observations and take their average. Things look kind of like the normal distribution or the t-distribution if we don't know the variance. And then we can say, we understand where these Z alpha or or Z alpha over 2 thresholds are, and we can use that to say how far out should this go. Can we go before? I think this is kind of unlikely. This is outside of the range of events we expect to get. Okay. So let's look at some examples in R, and hopefully this will also provide another perspective, and then great. Okay. You can, looks like you're still seeing that on Zoom, so great. Okay, so I'm gonna, everyone can see it at this font size. Okay. Okay, so what we're gonna start with, if you remember, the first hypothesis test we did was this Fisher's exact test with this lady so tasting tea. And so in this case, we had observed this 2x2 contingency table. And you can store this as like a matrix where the first entry is that, if you guessed the milk was first, and the second one is you guessed the tea was first. And again, on the rows, the first row is the milk was actually first, and then the tea was actually first. And so this is the case where there were 8 cups, and the lady guessed all 8 of them correctly. Okay, and so you can just store this. This is how you make like a matrix, a 2x2 matrix in R. Okay. And so then to run the test, there's actually, just like a single command you have to run, Fisher test, you pass in this table, it knows the size, it knows it's a 2x2 table, and it can look up the total counts in the table. And you have to say that the alternative hypothesis, right, that the baseline, the null hypothesis, is implicitly that it's going to be average, right? That it's going to be random, each guess is random. And the alternative hypothesis is that you can guess more things correct than you would if you were random guessing. And you input this here. You can also put less here. And this should be if you think that you would get less correct, and in this case you do much worse, I think you can do two-sided. Let's see if this works. This is if you think you can do worse or better. Okay. Okay, so let's see what this says. This is going to give the information about the p-value, which is effectively the probability that someone guessing at random would do that well or so better. Okay, and that's going to be about like 1.4% that you do it this well or better. The confidence interval, it's a little bit strange here. It's between 2. This is I think this value is out of 4, right? That the confidence interval is that you would get between 2.003 better up to infinity better, right? There isn't an upper bound here, so it's a little bit weird, right? And we'll skip what these odds ratio are, but it computes by default the 95% confidence interval as well with the same data, and it gives you this here. Let's again, we can recalculate. This is exactly the probability that out of the 8 choose 4 things, you got all of them correctly, which is 1.4%. Well, quickly, if you instead got 3 of the milk first correct and 3 of the tea first correct, the p-value is only about 24%. That means you guess randomly, you do this well or better, including getting all 4%, all 8 correct, 24% of the time. And now the confidence interval of the number out of 4 you got correct was 0.31 to infinity, if this was the actual case. If you do 4 misclassified cups, okay, so this is that the p-value is now 0.75. The probability you got this much or better correct is better than 75% if you do this at random. Let's see if we change this to two-sided, see if we get if now, right, so you could automatically get a confidence interval of the, okay, this is not, we'll do another example of this, but you automatically, you can calculate the confidence interval as well here. Let's just look at it. But since we're doing one-sided, the confidence interval here is one-sided again. And then if you guess them all wrong, the p-value is 1, meaning that you always do this well or better, right? So it's not very informative. Okay, let's look at another example now with when we're trying to estimate the mean, and we're assuming that the data is so it's going to be a normal or a Gaussian, so random variable. In this case, we aren't going to know the sample variance. Question? Yeah, so the C method here, so this is telling you it's going to be an array of data, and then you are kind of telling you the dimensions of the data. It's 2 by 2 here. Okay, and we're putting this inside of a matrix. It's just some way of casting. The way of doing matrices in R is it's not great. It's probably not as, Python has, I think, better functionality for this. MATLAB has even better functionality. So depending on what you want to do, I would say R is not great for dealing with matrix data, but it's okay. But there's a whole bunch of kind of machinery for dealing with matrices that are built in. So this is another data set that's built into R. That's why we're using it. This is on some early experiments by some Mickelson and Morley, who are trying to run an actual physical experiment to evaluate the speed of light. Okay, and we showed some plots of this earlier, and the speed of light is approximately 300,000 so kilometers per second. These values are after, it's slightly below that, and we've subtracted 299 kilometers per second from the data. And then the true speed after you subtract that is going to be this 792. Okay. And so and then there were a bunch of tests that, which you can, there are a bunch of experiments. They ran 4 experiments, and they were all not quite right, but they were kind of in like the right, so ballpark. They had the first 3 digits of precision right. But they ran a bunch of experiments, and this 4th one was the closest. And it came out with an estimate of about 820, right? The right answer should be 792. They got an answer of, on average, 820. And so, let's see, did I plot this someplace? So I thought I had a plot for this. So we want to check, like, what is the confidence interval they had around this, right? If we want to see the length they ran, if I do this, it'll print out the values. Let's see. So the sample mean was 820. The sample standard deviation was 60. And there were 20 different there are 20 different observations they made. Okay, so this is based on 20 observations. And so the standard deviation was 60, and the sample standard deviation. And we want to know, okay, is this going to fall inside of the confidence interval so that this is correct? Okay, and so we can compute the critical value, which is going to be, so actually let's start with a hypothesis test. Okay, and so there's the true speed, which is going to be our null hypothesis. This turns out to actually be we're going to actually use the actual true speed. This is 792. And our alternative hypothesis is that the parameter mu that they found is going to be greater than the true speed. All right, and we're going to model this with the normal distribution, that there's some normal distribution of it. Okay, so on kind of the homeworks, this is kind of, you'll be given some sort of setup on question 1 for the homework, and you'll be asked to produce like null hypothesis and alternative hypothesis, and maybe say, oh, it's following like there's like a normal distribution, which we're assuming it's following because it's going to be a continuous distribution. Okay, and so now we want to set up what is, if we think the alternative hypothesis is that the value we saw, 820, is going to be greater than the true speed. Okay, so we want to calculate a 95%, so a critical value. Okay, that how small could the true speed be? Let's put, or like how much larger would it need to be from the true speed for it to not, whatever they were observing from, not to be a faithful representation of the true speed of light. Okay, so we took the true speed, this critical value, right? The 95% critical value. We took the true speed, and we're basically adding to it the sample standard deviation of the average, right? So the sample standard deviation divided by square root n times the 95th quantile of, so the t of the distribution. We don't know the true standard deviation, so we need to use the t distribution instead of the normal distribution. Okay. Okay, and that said, the confidence, the critical value is like 815. Okay, so if this test was actually observing something that was representative of the true speed of light with some noise, but unbiased noise, then with 95% of the time, it should not have been larger than this value, 815. Okay. As you can probably put together already, we then tested the sample mean. Is it larger than the critical value? So when it is, 820 is bigger than 815. Right? So what should we do with the null hypothesis? What does this mean? The null hypothesis is usually that the null hypothesis should give a specific distribution, right? It should say, let's assume that they are observing data that is representative of the true speed of light and kind of from something that looks like a normal distribution. Implicitly, it's assuming, I said Gaussian here, but implicitly this is a normal distribution. Some from normal with sigma squared with sigma squared unknown. All right, so we're assuming it's from a normal distribution with the true speed of light as the center and the variance unknown. Okay, but this implies that it's unbiased, right? We're assuming it's going to be unbiased, but we don't know how noisy it is. But we estimate how noisy it is by calculating the sample standard deviation. Okay. Sure. Yeah. It's noise. As we end up looking at it, the sample standard deviation turned out to be about 60. Okay, and they're estimating quantity of 299,820 roughly, with a standard deviation of 60. So in some contexts, it's kind of noisy, but is it noisy enough that it might have been drawn from the true distribution? Right? Well, it's okay if it's noisy. Our goal is not to say, oh yeah, and we also hypothesize that the noise is below some threshold. That's not what we're hypothesizing. We're hypothesizing, is it probably an accurate representation of with some noise of the true speed of light, or is this a bias? So the alternative hypothesis is that there's some bias in their measurement that's giving them estimates of the true speed of light, which make it seem too large. Okay, so the alternative hypothesis is that we'd somehow made we're observing something which is not a faithful but unbiased noisy representation. We're observing something that is larger than the true speed of light. Where the way we're processing our data is off somehow, right? And if it was a good representation of the true speed of light, then we could keep sampling more and more data, and our kind of confidence intervals would get smaller and smaller. We'd eventually be able to resolve it. Eventually other experiments did resolve it, so down to this value. And I believe this is correct, 299,792.458 kilometer per second. How did they get that value? Through empirical observations, through some experiment that eventually was accurate enough and unbiased enough that they were able to confidently resolve it here. Okay, but these were like the first experiments. Okay, so did they? So should we kind of reject the null hypothesis or not reject the null hypothesis? Those are the two options. Okay, so the rejecting the alternative is not one of the two options we have. We can either reject the null hypothesis or not reject the null hypothesis. Not rejecting it means I don't have enough information to know whether it's fully from it, but I can't say it's off. So it's intentionally a double negative. And so I can either reject the null hypothesis or I can not reject it. And so refresher, our kind of observed value was 820. We said the critical value, which was the true speed, about 792, plus some value that we said that we're confident it should not be larger than this if it was this many observations with this sample standard deviation, so it shouldn't be larger than this at a alpha equals 0.5, right? Which means that 95% of the time we ran this experiment, it should not be larger than this value. And, 820, the sample mean, compared to this critical value, it is larger than that. Okay? Yeah. Yeah, great. So the right answer is to reject the null hypothesis, right? It's outside the confidence interval. It means that this early estimation of the speed of light was not unbiased, probably. We think we're 95% confident that it was not an unbiased view of the speed of light. Still pretty close, right? And it was a big kind of contribution at the time, but it still had some bias in it, as we later found out. Okay, at the time, this was the best estimate that we had. Okay, but we later found out that yes, it was probably a biased experiment in some way. okay? We can also get p-value, okay? What you would do here to get the p-value is I'm going to get a statistic, okay? And that's going to be the sample mean minus the true speed. And I'm putting this in a, look at how big this difference is, and then divide by this sample, so standard deviation, and then look at where this falls in the CDF. This is the PT. This is the CD. The P means the CDF, and the T means it's from the T distribution. And where this falls in the CDF, 1 minus that. Okay, so the T statistic is about 2, and the p-value is about 0.25. Yeah, question.
So PT, what is the P stand for?
The P, okay. D means it's the PDF, P means it's the CDF, and Q means it's the quantile. So this is the CDF of the T distribution.
Okay, so
it's the T distribution with degrees of freedom n minus 1, 19.
So when you put in T stat there, are you putting in some numbers, or are you putting in a function?
Yeah, so T stat is calculated right here. It's a constant value based on the observations. Okay, so this is the sample mean based on the actual data. I've actually looked at the data to calculate this. I've taken all the 20 observations, I've added them up, I've divided by 20, right? I've taken the true speed, which is my null hypothesis, and I looked at how big is the difference between these two. Oh, did I do there? Okay, fixed it. And then I said, well, I want this to be normalized, right? I didn't know what the units of that was, so I normalize it by my guess of the sample sigma. This is my estimation of the standard deviation of the distribution I sampled from, and then I took n observations. So for the mean statistic, the sample mean, I need to divide by square root n.
Okay, so PT knows the function.
Yeah, so it's doing the integral for us. It's looking this up in a table. Yeah. Yeah, then you would use the normal distribution. You do P normal, and you'd plug in. This would be, you'd use a standard normal because you subtracted off the mean of it. This should, under the null hypothesis, this is the mean, and you would have divided by the true sigma, if we knew what that was, divide by square root n, and that would have normalized it for this. So for the case of the sample mean. That's right. Good. Yeah. If you do not know the true variance, we just have a list of observations. We don't know what the true variance is. We need to use a T distribution instead. Yeah. Okay. There's a question on chat. Yeah. The critical value is, okay. So there's a question between the critical value we got here and the Rn, which is the right-hand side of the confidence interval, right? So Rn is so this is a good question. The difference here is the critical value only depends on actual data observations or constants were given. True speed were given as the null hypothesis. Sample sigma is from the realization of the data. Square root n is from is from the number of data points, and this is looking this up in a table depending on alpha. So the critical value is not a random variable. There's nothing random about this. these are based on observations. Okay. So whereas the RN value would have used a would have instead had at the middle if I put this with the sample mean, and typically the interesting thing to do, let's say instead I did the LN. This is the similar thing. This would be the sample mean, and now I can do the sample, so sigma divided by square root n times qt 1 minus 0.5 df equals n minus 1. So, okay, so this is kind of like so I want to do subtraction here. This is the left-hand side. Okay, so this is a similar thing, except this is the sample mean. So this is a lowercase l. So this is lowercase l. This is like the left side of the confidence interval with the actual realization of it. Okay, so if I actually observe the sample mean, and then I looked at the sample sigma, I said, this tells me how far away from that to go. And I say, and I'm now, so now I'd say, this is, my guess is I'm 95% confident that that if my experiment is actually observing something unbiased, right? So this is the, from the actual data. If I assume my experiment is totally unbiased, then that the true speed of light is greater. This is the lower bound, so that's greater than 797. Okay? If I wanted to do a two-sided confidence interval, then I would divide this by 2, right? And I would then I would divide this by 2, and this value, yeah, is even smaller. So it goes a little, that's saying it's within this, it's inside this distance.
So I don't know if you're saying this, but why did you call it critical value?
So the critical value is the threshold for rejecting or accepting a null hypothesis. Okay, and so I'm going to create this based on my true speed, and so, yeah, so based on these like observations, really what I should do is I should put the, yeah, so technically your test statistics should factor in, instead of using the sample mean, I should kind of factor in the sample standard deviation into the sample mean. But once I've observed this data, I can say that the sample mean would need to be larger than the critical value for me to reject the null hypothesis. So that's kind of the value that's critical for rejecting or accepting, or rejecting or not rejecting the null hypothesis.
So when you like push to yes.
Oh yeah. No, there are kind of these phase transition points and stuff in chemistry and other types of physics, and those are different. Yeah, yeah. Yeah, okay, great. Let's see. I can also, yeah, so we can also equivalently, we can calculate the p-value, right, which is 0.25. So, and if p-value is less than 0.05, then it's true, right? Okay, if I had instead said I want to be 99% so confident instead, right? I should have kind of said that ahead of time. I said, well, but well, like the p-value is not less than 0.01, right? So there is maybe, there's more than a 1% chance just based on this experiment that it was actually sampling unbiased, but there was just a lot of noise and I happened to get unlucky, right? But it's more than a 1% chance, but it's less than a 5% chance. Okay, so typically, if I use a 5% and I said to do that at the beginning, then I would have rejected the null hypothesis. Okay, if I had said, I want to be a critical value at 0.01 instead, or I only want to say a p-value is significant at 0.01, then I would say it's not significant, and maybe I do not reject the null hypothesis. Okay. All right, and okay, again, you can do this all in one kind of command, right? And this gives me this t-value, which I guess isn't exactly what we calculated. We calculated it in terms of the sample mean, and the p-value as we did before. It also gave this this confidence interval, which was between 4 and that the 95% confidence interval. If I do, let me see what happens if I do two-sided. So if I do, yeah, so it's looking at the t statistic instead. So it's saying, well, it thinks the t statistic, which is after I've normalized it, it's the 95% confidence interval is between negative 0.5 and 56. Okay, this isn't quite as useful. Okay. Okay. All right, let's look at another example. Okay. Yeah, question. Yes, right. So the p-value is like the probability this is a good way of thinking about that. That the p-value is the probability that rejecting the null hypothesis was the wrong thing to do. Okay, so if your p-value is 0.1, then rejecting the null hypothesis would be, you might reject the null hypothesis, but that would be the wrong thing to do like 1% of the time. 1% of the time, you would have actually seen something at that value or even more extreme, even if the data was actually from the null hypothesis, right? Yeah, so this is a great way to think about it. Yeah.
Is it between 0 and 1?
Yeah, p-value is going to be probability, so it has to be between 0 and 1. And the smaller the p-value, the more likely that the null hypothesis is going to be incorrect based on the data. Okay, well, let's go through this one more example. This is sampling from a Bernoulli distribution. Okay, and this is data from, say, 2012. I forget if Obama won Florida or not, but he was in the last. Let's test the hypothesis, the alternative hypothesis that he was not actually going to be the winner of Florida. Was below 50% of the people wanted to vote for him in 2012. And in the last poll, which is this Rasmussen poll, he was at 48%. It was 750 people. Okay. So now we need to create a null and alternative hypothesis, right? The null hypothesis is that it was at 50%. It was 50-50. And the alternative hypothesis is that the true value of the percentage of people in Florida who wanted to vote for Obama was less than 50%. Okay, so this is how so you would model this. And the nice thing about the Bernoulli distribution, if we are assuming this, that it's you either vote for Obama or you don't, right, is that you know what the variance is, or you can get a bound on the variance. I guess we use a t distribution here. Yeah, you can get a bound on the variance. It's p times p times 1 minus p. But if you don't know what actual p is, you don't know what the actual variance is. So we can, I guess we're going to use a like a t distribution. So here instead, okay. Okay, so this is we're going to again when you take an average of a bunch of Bernoulli random variables, they look like a binomial distribution over n divided by n, and this looks like a normal distribution. So we can then say that the average, the sample mean, is going to look like it comes from a normal distribution by the central limit theorem, and so then use a t distribution with the sample sigma here, okay? And so if we start with these values as input, we can create a critical value. Okay, so this is saying that this is the null hypothesis guess. Okay, and based on the sample sigma, the sample standard deviation. Oh yeah, we use sample sigma as the sample mean was 48, and we can directly calculate what the variance would be, which would be 0.48 times 1 minus 0.48, and then the sample standard deviation is the square root of that. Okay, so we can directly calculate this here. Okay, and then we can plug that in here to get. It's still an estimate of it, so we still need to use the t distribution to get the critical value. And so now this is like about 47%. Okay, and so this means that if we test, is the sample mean less than the critical value, it gives us the answer false. Okay, so should we reject the null hypothesis? Yeah. Okay, so we shouldn't accept it. We should use the double negative, embrace the double negative. We should not reject it. Okay, so we don't have enough evidence for just based on this poll to reject it, right? So if you're like Obama and you're thinking, this is in 2012, you're thinking, do I have any chance of winning Florida? Okay, and the poll said, okay, you're at 48%, but it was only 750 people. So you'd be 95% chance that you can't win Florida if the poll was less than, say, 47%. Okay, but it's not less than 47%, so you might still have a chance to win Florida. Now, it doesn't mean that you should accept the null hypothesis that you are exactly at 50%, but you don't have enough evidence from this one poll to say, I can't win Florida. Right? Does that make, so the distinction is a little bit, so you have the right idea, you should not reject it, but you shouldn't accept it either. That's implying something slightly different. Yeah, well, that's not quite the right reason, right? The null hypothesis is that Florida is exactly a 50-50 state. Exactly half the people want to vote for Obama. That's what the null hypothesis is. That might not be true. It might be 49% want to vote for Obama. But you want to say, is it definitely less than 50%? Right? If it's definitely less than 50%, then there's no chance of winning Florida. Okay, so then you'd say, oh, it's a lost cause. I'm not going to put any more ads in Florida because less than 50% of people, want to vote for Obama there. Okay, but you're saying it might be 50%. It might be bigger than 50%. It might still be 49%, but I shouldn't, it's not a lost cause. So I should not reject the null hypothesis, but it doesn't mean I'm accepting the null hypothesis. The null hypothesis either. The accepting it say, I totally believe it's a 50-50 state. Okay, where the the confidence interval would say, I observed 48%, and I think it's probably between, say, 45% and 51%. That would be kind of like the confidence interval. And 51% is greater than 50%. So there's a chance, the 95%, within the 95% confidence interval, there's a chance that he could still win. So it's still within the realm of possibility. Okay, yeah. Right. Yeah. Well, it came back. It's not conclusive that our null hypothesis, our base hypothesis, was wrong. Right. So it's kind of yeah. It's like we wanted to say determine whether we should that our alternative hypothesis that it's less than 50%, that was inconclusive. The null hypothesis was. We didn't say the null hypothesis was inconclusive. We said the alternative hypothesis was our data was inconclusive towards the alternative hypothesis. There are two hypotheses, right? So I want to make sure you're saying which one is inconclusive. The alternative is inconclusive. We did not make any judgment calls on the null hypothesis. It might be, it might not be. Yeah. Oh, okay, great, good. So it was good that we didn't reject the null hypothesis here, right? So even though it was less than 50% in the polling, it doesn't mean he was definitely going to lose. I know we're out of time. Let me just calculate the p-value here, right? You can also calculate the p-value that we should of the alternative hypothesis. It's about 13%. So it's saying, yeah, if we rejected the null hypothesis, we would have regretted this 13% of the time. And in this case, he actually did win Florida in 2012. So that fell in this like 13%. So great. So, okay. Hopefully this kind of gives you a sense of how to put these two things together, the confidence intervals and p-values, some examples. The homework will be good practice for doing this too towards the final as well. And we'll do a little bit on like linear regression on Thursday. That's the plan. And if you want to pick up a copy of homework 7 or the practice final, they're up front here. Oh. I have a question.